look at two things to say at the start. The first is that I apologize for giving this talk in part with view graphs instead of entirely on the blackboard. This is mainly because I didn't know I was going to be giving this talk until 2 days ago. And for the same reason, I apologize for a certain level of disorganization. The flip side of this is that this should encourage you to ask questions, because it's by no means an organized and polished presentation anyway. So please, at all possible times, stop and ask if I'm not clear, giving too much information, too little information, anything like that. All right, so what I want to do today is give you my view, which I warn you is slightly eccentric, on dynamical mean field theory and its cluster extensions. Right? And my understanding of this field has developed over many years with, through interactions with many collaborators, a fair number of whom are in this school. All right. So I don't think I'm going to get through everything that is here in the time we have, unless you're more boring than I think you are and don't ask any questions. But roughly, this is where I want to go. I want to spend a little bit of time putting what we want to do in the context of general many-body theory. All right? And then I would like to talk about the theoretical structure of dynamical mean field theory in a way which is slightly different from the way it's usually presented. And from this point of view, all of the different versions of dynamical mean field theory, it seems to me, are seen to be the same thing. So I will explain that and then try to give you a little bit of a flavor of what can actually be done in practice and what is the status of these approximations. And then finally, time permitting, I will give just a little bit of indication of some of the results that have been obtained. Okay, so that's where we're going. And let me start with why we're doing this. In other words, what is the need for approximations? Oh, and by the way, probably at some times I will want to write on the blackboard here. How do I control the lights? Oh, okay, so I should ask somebody when the time comes. All right. Okay, so we're concerned with fermionic many-body physics and indeed with the physics of electrons. Although, as you'll see in a bit, we are farther than we would like from dealing with real electrons, which of course have the long-range Coulomb interaction. Right? Now, the reason why dynamical mean field theory is, in my view, important is that there is an exponential wall which limits what you can do in studying an interacting electron Hamiltonian. All right? And what that means is that even though quantum mechanics is in principle just dealing with matrices, and there are many sophisticated computational methods for dealing with matrices, the size of the matrices that you need to get your hands on become rapidly too big for a direct attack on the problem. So here, let me say this in a very general way. All right? Let me take a quantum mechanical Hamiltonian. All right? And let me adopt some basis of single particle states. It's not important for this what they are, but just let me label them by some name alpha. Right? Then in second quantized notation, and again, please stop me if you're not familiar with second quantized notation, and I'm happy to explain it. A general Hamiltonian can be written in this form. So there's a part which is quadratic in the one electron operators. Right? This is just the single electron Hamiltonian, which is some matrix whose size is the number of single particle basis states you keep, and which can be diagonalized to give single particle energy levels. Right? Then there are various interaction terms. This is an interaction term between one fermion and another fermion, so there are 4 operators, 2 fermions. That's an electron-electron interaction. There could be 3-body, 4-body interactions and so on, which I've indicated by the ... the ellipsis there. Okay, so this is a general Hamiltonian written in a relatively formal way. Now, if one is doing condensed matter physics, then one is typically concerned with systems which are infinite or effectively infinite, so the number of basis states is in principle infinity. If you're doing chemistry, well, I've cheated you here slightly, but in chemistry, one is typically concerned with molecules which are small and finite. Of course, there's an infinite number of states if you consider electrons which are not bound to your molecule. But in general, for chemistry, you would consider a finite number, and for solids, an infinite number. Right? So this is a general Hamiltonian, and what we want to know from this Hamiltonian is the ground state and its excitations. All right, so far, so trivial. Okay, now, this Hamiltonian can be cast as a matrix. If you have a basis of single particle states, and then you have some number of electrons, you can make a basis of many particle states. And in that basis, this Hamiltonian is a matrix. And so the problem of quantum mechanics boils down to just diagonalizing a matrix. What's the big deal, you may say? Right? The difficulty is that if you have m orbitals, all right, then each orbital can have 0 or 1 electron, because electrons are fermions. You can't put 2 electrons in the same orbital. And therefore, the total dimension of the many-body Hilbert space is 2 to the power m. Each of the m orbitals can be in one of 2 states. So that means that the size of the matrix that you have to diagonalize grows exponentially with the size of your system. Right? So direct diagonalization becomes exponentially hard as the size of the system increases. And therefore, well, in practice, the size of matrices that you can diagonalize directly, even with advanced techniques and clever ways of getting the ground state, is not big enough to see anything interesting. A practical limit is about 30 in this language. Right? And because this is an exponential barrier, if I want to go from 30 to 31, that's a factor of 2 more, etc. Even though computers, the ability of computers to do things is increasing, this is going to increase only painfully slowly. So this is essentially a hard wall. This limit on what you can do directly is more or less fixed, and it's more or less not going to get bigger. Now, that said, there are various interesting things which you should know about, but which I'm not going to talk about here. In particular, density matrix renormalization group and its cousins, there are 2 nice review articles here, if you're interested in, are essentially very smart ways of diagonalizing things. And in fact, at least for obtaining ground states of some classes of systems, they call this statement into question. Right? So I don't have the time or the knowledge to explain this in detail, but what these methods do is formulate a very intelligent choice of basis, right, which localizes the quantum mechanical entanglement of the electrons in space in such a way as to make the giant exponentially big matrix that you have to diagonalize block diagonal with relatively small, or approximately block diagonal, with relatively small blocks that you can deal with. And so, in fact, for gapped systems, it has been proven, as far as I understand it, at least to the satisfaction of a physicist, that you can get the ground state in polynomial time, not exponential, in 1 dimension. And in dimension greater than 1, it's not proved, but it's, as far as I know, but it's widely believed that for dimensions greater than 1, generalizations of this will give you, in principle, polynomial time methods for finding ground states. Right? Now, I should say, by the way, when I say provably, as somebody remarked to me, the difference between a mathematician proof and a physicist proof is that a physicist proof has to convince a reasonable person, and a mathematician proof has to convince an unreasonable person. And when I say proof here, it's really physicist proof. Okay, so anyway, this is something which it's well worth your while to pay attention to. Because at least for some class of systems, there is at least the potential hope of beating the exponential barrier. Right? But I'm not going to discuss it further here. Okay, now, there's another method for exploring exponentially large spaces. This is a standard method which works for classical mechanics and indeed for quantum mechanical systems of bosons. And this is stochastic or Monte Carlo integration. All right? So basically, what you do in a Monte Carlo method is, if you want to calculate the expectation value of something, you can express it as the average over configurations of your system, denoted in some abstract way by some general 2 to the n dimensional coordinate x, of the value of the observable at each configuration times the weight, if you like, the probability that that configuration x occurs. And then you have to divide by some normalization, which is essentially the integral of this. Right? So this is just a reformulation of the task of finding some expectation value, including the ground state energy. And the advantage is that if you do a stochastic exploration of this integral, you can get reasonably good estimates in much smaller time. Other lecturers will talk in detail about how you do various kinds of Monte Carlo, but this is an enormously powerful technique for dealing in the general case, well, I'm not in the general case, in the classical mechanics case and in the boson case, with spaces of very large dimension. Okay, so the way you do it is basically, out of this enormously large configuration space, you select some number of points, m, with probability determined by this weighting function, and then you just evaluate this at the number m of points you have and divide by m, right? And this thing, more or less provably, at least in the physicist sense, converges like a power law in m. Right? So therefore, this sort of Monte Carlo calculation is really the method of choice for evaluating classical mechanics problems of this kind, or broad categories of boson problems. However, it doesn't buy you what you need for fermions. Right? And the reason is that if I go back, I'm sorry, to here, if you're applying this logic to a quantum mechanical problem, essentially, this x, the thing which labels the space of possible things you're averaging over, all right, is the space of all the many particle wave functions. Right? And you know for fermions, the wave functions are anti-symmetric under exchange of particles. Oh, at this thing, I should have said, this is the space of all wave functions, and this is essentially the wave function amplitude. So for fermions, you know that the wave function has to change sign if you interchange any two fermions, no matter how far apart they are. Right? And that minus sign means that this thing W is not always positive. Right? And if it's not always positive, it's not a probability. So you can't do these arguments. To put it slightly differently, in the fermion case, because this isn't always positive, the convergence of this integral comes not by adding up a variety of positive things, some of which are exponentially bigger than others, but by adding up a bunch of plus and minus things. And convergence of an oscillating sum is a disaster. All right? So, of course, there is a technical thing you can do, given that this isn't always positive. You can say, all right, let me define a new weight, which is just the absolute value of this thing. Right? So that's positive. So then the object that you would like to average is the absolute value times its sign, times whatever quantity you want to consider. Right? So that means that in particular, the partition function, which is the average over all these weights, I can write as the average of the sign of the weight times the weight. Or if you prefer, this is the expectation value of the sign times the partition function that I would get just from this positive weight. Right? So that means that if I want to compute the average of some quantity, A, this is just algebra. this is the formula that we had before. I replace this guy by its absolute value. That means I get this sign. This partition function is the partition function of the positive part times the expectation value of the sign. So this is the object that I need to compute. The average of my observable times the sign of the weight with respect to this absolute value probability measure divided by the expectation value of the sign. Okay? So that's what you do in practice if you want to do fermion Monte Carlo. Right? And the problem is that this sign becomes exponentially small as your system size goes to infinity or your temperature goes to 0. Right? And there's a simple argument for this which is not clearly published anywhere to my knowledge. I first heard about it from Fakhar Assad. There was something like this published by David Sepperly. And the argument is this. Just look at this guy for the moment, this expectation value of the sign. From the definition, that's the ratio of the partition function of our fermion problem divided by the partition function of this thing with the absolute value statistical weight. All right? So you know roughly what the partition function is. Partition function is exponential of free energy divided by temperature. All right? So this ratio is therefore the ratio of exponential of free energy of a fermion system divided by temperature divided by exponential of the free energy of a, quote, boson system, something which has the same Hamiltonian as my fermion system, but I just took away the sign, divided by temperature. Right? Now you know, because of this absence of the minus sign from exchange, that free energies of boson systems are always less than free energies of fermion systems. All right? Therefore, because this is less than this expectation value of the sign is the exponential of a negative quantity, and a negative quantity divided by temperature. So that's why. And because the free energy is an extensive quantity, the sizes of the fermion and boson expectation values grow, of the free energies grow proportional to the size of the system. Therefore, this ratio is exponentially small in something which is some number which you don't know times the size of the system divided by the temperature. So therefore, even with Monte Carlo methods, you have an exponential barrier to performing computations. Right? And again, as a practical fact, this exponential kills you when trying to do fermion Monte Carlo before you can get to interesting system sizes. Right. So that's the most important thing I wanted to say in the first part of this talk, is that generically, in fermion problems, there's an exponential wall of computational complexity. So any direct attack you do on the problem hits this wall in practice before you get to the interesting sizes and temperatures that you need. Yes?
So that last argument of yours
Yeah.
says that the expectation value of the sign is always positive.
Actually, no. There can be an overall minus sign. All I care is that its magnitude is, all I care is that the magnitude becomes exponentially small. Because remember, I should have stressed that a little more. Here, you see that you have to take whatever you compute and divide by this, right? So as you have errors in here, dividing by this will amplify those errors. Okay, so, correct. Exponentially, that's the point, that the expectation value of the sign is e to minus something proportional to the system size, because it's extensive, divided by temperature. Right? And again, different methods will give you different prefactors to that basic thing, which is system size over temperature. And clearly, there are advantages to attempting to optimize what's in that. But generically, there's an exponential barrier, and it will kill you. Right? And you know, it's a fundamental rule of computer science. If it's a power law, you can deal with it. And Moore's law will eventually solve your problem. If it's exponential, not. All right. So that brings me to dynamical mean field theory. And my view is that its great power is that it's an indirect approach all right, in which you obtain some subset of the full set of information that you might want by solving a different and simpler problem. It's still limited, ultimately, by the same exponential wall, right? But by arranging what you want to calculate intelligently, you can maximize the information that you want to get before you hit this wall. All right? And that's really what this whole theory is about, is maximizing the information you can get before the exponential problems kill you. Okay, so that's the general philosophical part of this lecture. So now I would like to turn to a general theoretical formulation of dynamical mean field theory, which, at least in my view, makes the cluster extensions quite transparent. Right? And as I said, it's an indirect approach in which what you do is you express some aspects, a limited subset of the solution of the physical problem in terms of the solution of an auxiliary problem, which is simpler. Right? So before describing that, the dynamical mean field theory, I find it very useful to discuss density functional theory, which is a closely analogous case. Now, I'm assuming in saying this that you more or less know what density functional theory is. And again, if that's not the case, please stop me and ask. Right? So how does density functional theory work? There was a theorem proven by Hohenberg and Kohn in 1963, I believe, and published in 1964, which says the following thing. It says that if you take a general interacting fermion problem, I wrote electrons here, but interacting fermion problem, all right? Then for that problem, there exists a functional, which I've called phi, of the fermion density, and a functional is an object which eats a function, in this case the density, and gives you a number. Right? So they said there exists a functional of the electron density, which has three interesting properties. It's minimized at the physical density, whatever that is. Its value at the minimum gives the ground state energy. And finally, it's the sum of two parts. One part just says what problem your fermions are dealing with. If you're dealing with a solid or a molecule, this is just all the potentials of all the ions. Right? And the other part is universal, meaning that it is the same for all values of the external potential. It depends only on the force law between the fermions. In the case we care about, that means it depends only on E squared over R, which is the Coulomb interaction. But if you have a general fermions with some general interaction, it would depend on that. Right? So if you want a limited subset of information about your problem, namely the density and the ground state energy, then you can solve a notionally simpler problem, namely minimizing this functional. Right? So that's an example of focusing on a reduced subset of information, which you hope you can get by a more simple means. Okay, so that means that to get the energy and density, all you have to do is go back to this, stick in whatever your potential is, and minimize. Great. Right? Unfortunately, we don't know the universal part of the functional. And at the time of the Hohenberg and Kohn paper, we had no idea how to minimize it. So it was therefore an appealing formal development, but of no practical use whatsoever. So the breakthrough, which was done in '64 and published in '65 by Walter Kohn and Lou Sham, who were shown here, was the following. First, they found a way to carry out the minimization by solving an auxiliary problem, which is just one electron quantum mechanics, which I'll explain in a moment. All right? Plus a self-consistency condition. Right? And second, they found appealing and, while not exactly precise, relatively useful approximations to the universal function. So how does it work? What they showed was that you can minimize this function by solving a single particle Schrodinger equation, which has this form. So this is just the usual interaction with the ions. This is the self-consistent static electric field of the electrons. And this is an extra potential, which depends in some way on the density, all right, and which is obtained from this universal function. Right? The self-consistency condition is that you solve this single particle problem. You fill up the states to the Fermi level. You compute the density from these states, and the density you find has to be the same as the density in here. Right? So what you do operationally is you guess a density. You write, that gives you a potential. You write the equation, you solve it, you compute a new density, you stick it back in here, and you keep doing that until it becomes self-consistent, and that works. Excuse me. Notice also that in carrying this procedure out, you never need to know the universal functional itself. You just need a recipe for obtaining this potential. All right. So that, in a nutshell, is density functional band theory. And the only other remark I wanted to make was that this is an auxiliary problem. As a matter of fundamental principle, the eigenfunctions and individual eigenvalues don't have any physical meaning. They're just a tool, cogs in a machine, whose job is to give you the total energy and the total density. Of course, as you have seen in this course and other places, in many cases it's both tempting and reasonable to ascribe physical meaning to these eigenstates. But in principle, this is just a machine to give you a limited set of quantities, namely the energy and the density, from which you learn a lot. Right? So this is a way to beat the exponential wall. Right? If you're interested in a limited subset of quantities, in this case the ground state energy and the charge density, you can obtain that information by solving a simpler non-exponential problem plus a self-consistency condition. All right, so that's density functional theory. And now I want to discuss dynamical mean field theory by analogy. All right, so that I sort of said. Okay, so dynamical mean field theory, in my view, you should think about as conceptually the same as density functional theory, except that instead of the electron density, you have the electron Green's function or self-energy. Right? But the logic that you use, so the way you think about it, is the same. All right. So you've probably seen this, but I thought I would flash, and I can provide these view graphs if people want them later. But there's a series of references which I personally at least have found very useful in understanding this. And I guess that probably, well, here, I'll just leave that up for a second so you can write them down if you want. All right, so the dynamical mean field theory then is analogous to the Hohenberg-Kohn theory in this way. If I start with a Hamiltonian, right, which has electrons, a quadratic part, an interaction part, then in close analogy to the Hohenberg-Kohn density functional, and in fact this was known a bit before, the relevant paper was 59, I believe, there is a functional of the electron Green's function, or self-energy, which is a sum of two parts. A universal part, which depends only on the force law between the electrons, and a part which I've written in a formal and not very transparent form, which tells you which problem you're looking at. This encodes the bare mass of the electrons and whatever external potential you have. So this is a functional, which I've chosen to write as a functional of the self-energy, right? And it has the properties, as I say, that it's the sum of a material-specific part and a universal part. It's extremized. The extremum is it's a saddle, not a minimum, but it's extremized at the self-energy or Green's function corresponding to the solution of the physical problem. And from the value at the extremum and fluctuations around it, you can get not just the energy, but thermodynamics and quite a lot of information about response functions. Right? And the reason you can get more information than density functional theory is that the basic moving part inside is not just a single scalar quantity. The density is a function of position. It's a self-energy which is also a function of frequency, so it contains information about excited states. All right. So this is the many-body analog of the Hohenberg-Kohn result. Or if you want to discuss things in proper historical order, the Hohenberg-Kohn result was the density, was the ground state energy and density version of the Luttinger-Ward functional. Right? And just as with Hohenberg-Kohn, oh, I should have said, actually. Yeah, so I got slightly out of order, but just to say, just as with Hohenberg-Kohn, this was not very useful because we didn't know, except via perturbation theory, what the universal functional is, and we didn't know how to carry out the minimization. Right? And then I'll come back to this in a second. So the key breakthrough, following important earlier work from a somewhat different point of view by Metzner and Volhart, was done by Antoine George, who is here, and Gaby Kotlyar, who I guess is not. And in my view, the crucial importance of their work was they took the analog of the Kohn-Sham step for this problem. In other words, they showed how to perform the extremization by solving an appropriate impurity problem. And they produced something which is analogous to the local density approximation for the exchange correlation function to make the auxiliary problem tractable. So what dynamical mean field theory is the Kohn-Sham idea applied to the universal functional of Luttinger-Ward. Okay, so now let me just go back, because I think I'll need this briefly. First, this universal functional is actually defined originally in terms of Green's functions as the sum over all vacuum-to-vacuum skeleton diagrams with appropriate symmetry factors. So there's a Feynman diagram definition of this thing, which only involves the Green's function, which is a mathematical object. It's a functional of the Green's function, and these dots, which are the force law, the interactions between the fermions. Right? So that's the sense in which it's universal. Right? And you can see also, because it's a sum of an infinite diagrammatic series, you can't really calculate it. Now, as you can more or less see from this, if you differentiate this functional with respect to the Green's function, differentiating it with respect to the Green's function is like breaking one of these lines. That gives you a self-energy. Right? So the self-energy is the derivative of this functional with respect to the Green's function. So that means you can make a Legendre transformation like this to get something which is a functional of the self-energy. Right? Because if I differentiate this guy with respect to the Green's function at fixed self-energy, this gives me the self-energy, this gives me minus the self-energy. So it's not a functional of G, it's a functional only of the self-energy. Right? You can view these theories equivalently as functionals of G or self-energy. I find it much more convenient to view it as a functional of self-energy. Okay. So similarly, from this definition, the derivative of this guy with respect to the self-energy gives you minus the Green's function. And the stationarity condition of this is that the derivative of the entire function with respect to the self-energy, as you can see just by putting these three things together, demanding that this is stationary, well, if I take the derivative of this guy with respect to the self-energy, I get minus G. I take the derivative of this guy with respect to the self-energy, I get the inverse of that, which is the Green's function. So the stationarity condition is just the definition of the Green's function in terms of the self-energy. Right? And I'll come back to that in a second. Okay. So as I said, so far this is all formal blah, 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 which was not really useful beyond perturbation theory, because before Kotlyar and George, we didn't know how to construct the functional or how to carry out the extremization. All right. So now I'm going to give you my version of their idea. Right? If we go back to this system, which has a single particle basis of m states, the self-energy is some m by m matrix. You can put in symmetries and discuss how many independent components it has. But so it's some order m squared in general functions of frequency. Right? So this is a general self-energy written in some arbitrary basis. Right? And because m, the size of your many-particle Hilbert space, grows exponentially you're going to have an enormous number of functions of frequency. All right. Now, so what dynamical mean field theory does, the essential approximation, is it parameterizes the general self-energy, which I've written here, in terms of a small number of functions of frequency. So here I've written a very general, so general that it's basically useless, but I'll come back to more specific forms later. But a general way of expressing this, which is a capital M by capital M matrix, in terms of a presumably smaller number of quantities, n by n, and so on. In the same way, there's a variety of choices of this thing, which can be used to construct different kinds of dynamical mean field approximations. But the essential idea, common to all of them, is you have your self-energy of the full problem, which is a very big matrix, expressed in terms of a small number of objects. All right? So you're obtaining a limited class of information, in this case, some kind of coarse graining of the self-energy. All right? But at a much lower computational cost than solving the full problem directly. Yes? Well, that's your choice. No, but the reason why this is effective is that you can get quite reasonable information in many practical cases with an n which doesn't scale with m. All right? But it's also a very valuable question because I forgot to mention. All right? Clearly, as n goes to m, you recover the exact theory. All right? And your approximation will in some sense get better and better as n increases. Right? But then if you just go back to thinking about the exponential wall, which is present in all of these calculations, all right? The crucial issue is really how big an n can you afford to deal with before you hit the exponential wall? And can you get useful information with that level of n? Right? And this is a question which doesn't have a hard and fast mathematical answer. Right? You're doing an approximation, and it's very rare that there's an a priori estimate of how good the approximation is. All right. Now, there's something else which I'll come back to and give you a more explicit example later. But there's one way in which this nice analogy has cheated you. You not only approximate the self-energy, but in ways that I'll explain later, you have to truncate the interactions. Okay, so first important point. Conceptually, in my view, it's not useful to distinguish between single-site and cluster dynamical mean field theory, or between the different versions of cluster dynamical mean field theory. It's all the same thing. It's just a question of how many of these guys do you use and what you put for this. They all live under the same theoretical umbrella. They're just all minor variations on the same thing. Okay, now, so how does this work? What you do, in essence, is you take your self-energy, which is this, and you stick it into your universal function. Right? That means that your universal function is now a functional of some smaller number of quantities. So it's a functional just of the n squared approximates and not a functional of the full self-energy anymore. So same universal functional, but now what's really inside it is a presumably much smaller number of moving parts. All right? So that means that your universal functional can be viewed as a functional of a finite, small number of functions of frequency. Right? And now let's ask, in very general terms, what is that? Right? So the argument is that you can view this as the universal functional of some theory which depends on time, because these self-energies are functions of frequency, but has no explicit dependence on space. You can view these small number of things as just flavors, different labels of particles. So that what this is the universal functional of some theory, which is 0 space, 1 time, and some number of flavors. We still don't know what that theory is, because we don't know what the general universal functional is. But it's the theory of some 0 space plus 1 time dimensional model plus some flavor indices. All right? So if you view it that way, then the usual arguments say the derivative of this with respect to the approximate self-energies gives you the Green's function of that 0 space plus 1 time dimensional model. All right? Now, what is a 0 space plus 1 time dimensional model? Well, in condensed matter physics, we could view this or call this a quantum impurity model. All right? If it's 0 space dimensions, it's a finite region, one site, if you like, with some indices, with interactions. The fact that it has a non-trivial time dependence can be expressed by saying that it's coupled to a non-interacting bath. So here I've made a sort of pictorial representation. This is my 0 space dimensional site with 8 internal flavor indices coupled to some non-interacting bath. So that's the general class of problems that we have to solve. All right? So finding the Green's function of this 0 space plus 1 time dimensional theory, whatever it is the same thing as doing that. Right. Notice again, in close analogy to density functional theory, this quantum impurity model, like the Kohn-Sham equations, has no real status except that it's a machine for generating an approximation to the self-energy. Right? But also, as with the Kohn-Sham eigenvalues, it's very tempting, and indeed reasonable in many cases, to give it a physical meaning. Okay. So now to specify the quantum impurity model, you need two things. The first is the interactions, which connect these states. Right? And these interactions are just, and I'll explain this by an example later, the appropriate truncation of the interactions in the original model, and a non-interacting, that is to say, bare Green's function. Right? So you have those two things. You have a quantum impurity model, which you can imagine solving. So then you can compute the Green's function and the self-energy. Right? Okay, and in fact, I guess I'm just going to skip this for the moment. So this is the last bit of let's say, pure formalism. So what I told you was that if you approximate the self-energy in this way, then the universal functional of the self-energy becomes a universal functional of your small number of approximants minus, this is what we had before, this is the self-energy expressed in terms of these approximants. So I now make this stationary with respect to these approximants. Here, just give me 1 second, and then I'll come back to your question. So I make this stationary with respect to the approximants. The derivative of this gives me the Green's function of the quantum impurity model. If I take the derivative here, I get the inverse times this function, f, which tells me how to put the approximants together to give me the real lattice self-energy. So I have this equation demanding that the free energy be stationary, tells me that the Green's function of the quantum impurity model is equal to some appropriate average determined by this function of the Green's function of my original model with this approximate self-energy inside it. All right? So this is the dynamical mean field self-consistency condition, and you can manipulate this into something which tells you what the non-interacting Green's function is. All right, now there was a question?
Yeah, so these AB levels are the site levels of your cluster?
If you like. The way I would put it again is that just you have, yes, you can view them as the site labels of your cluster. In a more formal sense, you have a subset, a small number of flavor indices in your quantum impurity model. But yes, they label the number of approximants that you need.
So you are viewing your finite size cluster as a single quantum impurity which has some different like spin-like flavors.
Yes, flavor labels. Yes, exactly. But yes, so then you can make a physical analogy specific to a real impurity model with sites that map onto the sites in your lattice. You can have them represent points in momentum space or other things, right? Now, part of the reason that I went through this, and you'll see this again in a few moments, right, is that there's basically at this stage of the theory, there's really two things that we know how to do within this formalism. And I personally can't believe that these are the only two things that can be done. Right? So I believe that some more creative theoretical thought about what are good ways to approximate the self-energy in interesting general classes of models would be very much worthwhile. That has not yet been undertaken, at least not been undertaken successfully. But I think that there is more structure there than has been revealed so far. Okay, so this is the analogy. To be precise, the density functional of Hohenberg cone is the Luttinger-Ward functional of many-body theory. The cone-sham equations are the solution of the quantum impurity model. The particle density is the electron Green's function or some projection of it. Right? And the reason that this is good is that, as you have heard already in this course, school, I believe, and as you will hear in more detail later, quantum impurity models are something that we can solve much better than lattice models. There's still an exponential wall, which you will hit eventually, but you can go quite far before you hit it. So in practice, just as you do with density functional theory, you guess the hybridization function or Baire-Green's function. You solve the quantum impurity model. You find the self-energy. You use that to construct the lattice self-energy, and then you put that in the extremum condition. That updates the Green's function or hybridization function. And then you continue until convergence is reached. Right? And this procedure actually works and works reasonably well. Okay, so this is what I said before, that in formal terms, what you're saying is that you construct an approximation to the full self-energy matrix in terms of a presumably, hopefully, much smaller number of functions of frequency, which are determined from the solution of an auxiliary problem, which can be viewed as a quantum impurity model, plus a self-consistency condition. All right. Again, these impurity models are still interacting quantum field theories involving fermions. So there is still an exponential wall that you will hit at some point, which limits what you can do. And the key practical question is in all these approximations, for a feasible value of n, can you get the physics information you want? Okay. So that was very general formalism. If there are no questions about this, then I would like to go to some examples. Yes?
So what's the basic difference between single site and cluster?
Well, you'll see that in a second, but really, in single site DMFT, this F is just, you just have one index here.
Actually, I would rephrase it. What are the advantages?
Okay. Well, basically, solving these quantum impurity models gets rapidly harder as the number of approximants increases. Right? So from the point of view of actually being able to solve things in a finite time, you want to make this as small as possible. Right? On the other hand, from the point of view of maximizing the information you have about your system, you want to make it as big as possible. So it's that trade-off which you have to do. And again, there's no hard and fast rule. Right? In different circumstances, different sides of this trade-off will be better or worse. Right? But basically, again, you always in this business, you have a tension between wanting to reduce the number of approximants because your computational cost increases rapidly as your n increases, and increasing the number of approximants to get something which is more accurate.
Zero space approximation is nowhere. That means the zero space approximation is still here.
Yeah, but again, that's just the statement that it's convenient to view these things as flavor indices, if you like, of a 0 plus 1 dimensional quantum field theory. Yes?
So within this formalism, multi-orbital is exactly same
Yep,
as
yep, yep, yep. Well, yes. From this, you know, sort of eagle's eye view, flying high above the landscape, it's exactly the same. There is an important issue concerning actually solving this, which is that actually it's basically the same. But one way to look at the problem of fermions and fermion minus signs is that exchange of fermions becomes important if there's a loop, right? And in at least reasonably high symmetry situations in multi-orbital but single site, you can arrange things so there are no loops. Whereas as you go to more sites, you very rapidly get into a situation where there are loops, and therefore you have fermion minus sign problems, even in your quantum impurity model. That's the place where. But from a formal point of view, single site, multi-orbital, multi-site, it's all the same thing. It's just a question of what you use for this f function. Okay, so this is what I said before. These questions in red, I think there is not yet a fundamental answer. Right? So I at least don't know what the universe of all possible choices of this is. And therefore, I don't know what the optimum is. And I think it's worthwhile thinking about this. There may be creative, different ways to construct these self-energy approximations than have been formulated so far. Right? Because the history of this field is that people were led both to dynamical mean field theory and its cluster extensions by somewhat different and more physically motivated arguments. Right? Okay, and another point is that this is some kind of big matrix in a space which relates your single particle basis of the model you really want to solve and your choice of approximants, right? So the form of that matrix, and therefore the computational and practical advantages, will presumably depend on your choice of basis. There are almost surely more and less smart choices of basis. And again, people have not carefully thought through how that works. So that's why I would really stress what's written in red at the bottom there. Okay, so here are the examples that we have. They go by names which are made up for historical reasons. And my view is just don't ask what they mean. Just view those things as labels. All right? Now, I'm going to introduce them in the context of the most studied case, which is the Hubbard model. Here's a nice picture of Mr. Hubbard. You've all seen the Hubbard model. It's a periodic lattice of sites. Each site can hold 0, 1, or 2 electrons. And there's a purely local, that is to say, on-site interaction. All right? So I can write it in real space or momentum space. And in this model, there's a self-energy, which is therefore a function of frequency and either spatial index or momentum index. Okay, so this CDMFT thing was introduced in this paper by Kotlyar, Savrasov, Palsin, and Biroli. And it focuses on the self-energy in real space. What they say is the following. Take a lattice. I've drawn a two-dimensional square lattice here, but you can do whatever periodic lattice you want, or even non-periodic lattice. All right? And tile it with equal-sized cells. So here I made cells with 4, but you could do it with 2 or with 8, anything that tiles it. Right? So tile it with equal-sized cells, which I'm going to label by some index capital J. All right? Now I take my self-energy, which is a matrix in real space. All right? And the approximation I do is I throw away every term in the self-energy which couples sites in different cells. So I could keep, for example, the term which couples this site to itself, the on-site term in the self-energy. I could keep this term, which couples this site to this site, but I would not keep the term which couples this to that. So that's an approximation. Now, if I have a translation invariant system, All right, I've now replaced my big self-energy matrix by just, in this case, basically three things: on-site, first neighbor, second neighbor. Right? So that approximates the entire large self-energy matrix by, in this case, three things. And again, you could approximate it in different ways by choosing a different pattern of tiling. Right? And which pattern you choose is your choice. It's, again, a trade-off between computational complexity and physics. All right? Notice that if n is different from 1, that is, if you keep anything beyond the on-site term, you've broken translation invariance because you keep this term in the self-energy, but not that one. All right? And these two bonds are equivalent. This tiling is an arbitrary thing. So this formalism, therefore, intrinsically breaks translation invariance. That's the price you pay, one of the prices you pay for getting this simplified approximation. All right? That's what I drew here. You keep the thing represented in the heavy circle. You don't keep the thing represented by the dashed line. All right. So now we can just write this problem in a supercell basis. Just introduce a spinor operator, all right, which for each site j has, in this case, n goes from 1 up to 4 sites. So I just assemble electron operators for each of these 4 sites in some cell into one big object, which in this case would be a 4-entry spinor. Then I can rewrite my Hubbard Hamiltonian in this spinor thing. My hopping term now has one part. I should have written this as I and j, but that connects 2 sites. Oh, that's here, right? So I have an on-site term. I have a term which connects different cells, which is a matrix, in this case 4 by 4, because right? And the same on-site interaction, right? So that means, in terms of the notation I gave you before, this general function, right? We start with a site basis for my original problem. That's I and j. A and B are labeled these guys. And what this is a delta function of supercells times a unit matrix, which says that A maps onto this, 1 maps onto this site, 2 maps onto that site, 3, 4. Right? So that's how that fits into this general formalism. Then I have a Green's function, which is, again, a n by n matrix in this supercell notation, and a self-energy, which is now purely local in this supercell, right? Meaning it has no matrix elements that connect, say, this to this, but is some matrix inside the cell, right? So this is a very concrete example of this approximating the self-energy by a small number of other functions, all right? And in the self-consistent equation, you solve your quantum impurity model, which is now is a single site with 1, 2, 3, 4 flavors in this case. That gives you a 4 by 4 Green's function. That should be equal to the lattice Green's function expressed as a matrix in this supercell notation and evaluated on site. That's here. Okay. So then there's a bunch of mathematical blah, blah, blah. And so if you can solve this n by n quantum impurity model, then you get these approximations to the self-energy. Now, you will notice, as I said before, that this thing explicitly breaks translation invariance. All right? So there's 2 ways to think about this. One way, which is what I prefer, is just to accept it. This is part of the price you pay for this approximation. All right? So you calculate with it, all right, and you calculate only quantities that are not directly influenced by this broken translation invariance. To the extent you can do larger clusters, you can try to guess from them how you would go back to the infinite translation invariant case. But so for things like, you can get there for easily things like energy, some nearest neighbor correlations, and so on. All right? And local excitation spectra. There's another point of view which says that what you should do is what's called in the literature periodize. You should take this thing which is not translation invariant, right, and then recombine the results to construct a periodic function. Right? So my view is that you should just do this. And anything here is ad hoc. But this is not a view which is widely shared. Wait, I'm sorry, let me go back. So there's actually, I'll come back to this in a second, but in this particular case, right, and stop me if this is not, if I've misinterpreted your question, but really you keep this term in the self-energy and not that. So that breaks translation invariance. So the periodization idea is to somehow combine some fraction of this, take some fraction of this and put it here as well, right? That's what people try to do, right? And they're really, so in general, what you do is more or less you construct some quantity, right, which you regard as a function of momentum in the full Brillouin zone of your solid, right? And you do it by Fourier transforming things only over sites which are inside your cluster, right? So you do this kind of approximate Fourier transform and interpret this as a periodic function in the lattice, right? And then there are various different quantities that you can use. You can use the self-energy. You can use the cumulant, which is more or less the inverse of the self-energy. You can use the Green's function. And there's a whole literature which you can read about here where people discuss which is the best thing for different approximations. Here's a particularly detailed study. I'm sorry I didn't have the journal reference. I believe this has been published in Physical Review B, actually. They did a relatively extensive study of different sizes, different kinds of periodization. Again, my belief is that you should just be a numerical purist and not get involved with that. My belief is that broken translational invariance is just a fact of life in this approximation, and you should simply live with it, and that these other things are ad hoc. But as I say, this is not a widely shared view. Okay, but just to say, again, because these are my lectures, the thing which makes me nervous is here's a 4-site cluster, all right? What periodization attempts to do, for example, is guess the self-energy at this momentum point, which is pi over 2, pi over 2, by taking the cluster momenta, the things you can get by Fourier transforming within a 4-site cluster, which are this, 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 and this, right? So it gets something here by trying to interpolate from these, right? And it may very well be that the physics of this point is simply completely different than the physics of any of these points, and therefore an interpolation is simply a bad thing. That's what makes me nervous about periodization. Okay, now there's another interesting point, which comes back to the thing I said before about appropriate interactions. All right? What you do in this CDMFT thing is you approximate your universal functional, all right, by making diagrams which involve Green's functions, which are local in this supercell basis. To go back to my little picture here, well, sorry, all right. Right? Because you're not including this, right, in constructing your universal functional, if you want to view it as a functional of the Green's function, you're not including Green's functions that go across here, right? Now, if you're not including Green's functions that go across the boundary between your two supercells, you also cannot include interactions that go across the boundary of your supercell. If you have an interaction between this and this, then that will connect what's happening here to what's happening here, and that will destroy this local approximation. So therefore, in constructing this universal functional, you would have to keep only the interactions which connect things inside this box and not keep these interactions. Right? So that's what I mean about, well, no. But you're doing some kind of violence to the long-range interactions. You can see that if you have a purely local interaction, like the on-site Hubbard interaction, then there's no problem whatsoever, right? If you have longer-range interactions, you keep this one and not that one, right? So that's, again, part of the price you pay for this approximation, right? And that's what I meant when I remarked back in the formal section about in defining this, you have to keep the appropriate matrix elements of the interaction. Okay, so there's a very instructive example which we did back when we were interested in this dynamical mean field theory for molecules, like what Cedric Weber talked about the other day. So this is the paper. So what we did was, in a chemist toy approximation, solve chains of hydrogen atoms, right? And the chemist toy approximation is what we mean by a hydrogen atom is we keep only the 1s state on each hydrogen atom. We don't keep 2s, 2p, continuum states, anything else, just only the 1s state on each hydrogen atom. But we kept, at least on the starting level, all the matrix elements of the Coulomb interaction between electrons in these states. Okay? So that gives you some Hamiltonian, where you just keep the 1s states on each hydrogen atom. You take all the direct exchange matrix elements of the Coulomb interaction. You get some problem. All right? And of course, the values of these Coulomb matrix elements depend on how far apart you put your atoms. And then we did, chains and rings and little tetrahedra and various things. All right? So again, what CDMFT does is you write your self-energy in real space. Now, 1, 2, 3, 4, just label our atoms. What CDMFT does is it says you keep just this, 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 this. That would be single site, or two site. You would keep this, 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 and so on. All right? And then, in the same way, you treat, as André-Marie Tremblay said when he was talking about superconductivity, orbitals outside the active blocks. You can treat the interactions and the self-energy by Hartree-Fock. So that gives you a problem, like this, right? So here we have two sites. We keep V12, the Coulomb energy. We have two sites here. We keep V34, but we treat V23 just by Hartree-Fock. Right? And again, that's the price you have to pay for using these kind of methods. All right. So you do this, and then this is a picture with more information than is particularly interesting. But this black curve is essentially the exact solution to this problem obtained by this density matrix renormalization group. And what's plotted here is energy against hydrogen separation. Right? These other things are various stuff. The interesting two are the following. This, which is notation I don't approve of, but I lost the fight with my graduate student, is single-site dynamical mean field theory. Right? This purple thing is this two-site CDMFT with doing violence to the intersite interactions in the way I explained. Right? So what you see is that the single-site, all these approximations give you approximately the correct curve of the binding energy. All of these differences mark these approximations as very poor from the point of view of chemists. Right? These accuracies are not good compared to what chemists really want. But notice that the CDMFT result, which is here, is really quite close to the exact result and much better than the single-site result. Right? So there's something funny. This approximation is in some devious way very smart. Even though it's keeping dynamically this interaction and not that one, somehow it treats this, it has enough more of this effect to compensate for a large degree of what it's left out. Right? So it's surprisingly smart at smoothing out this obvious trouble with the interaction. Where are you? No. I'm sorry, it's one of these things that Gustavo Scuseria did, and I don't remember what it is. From this point of view, it's something that our chemist colleagues wanted to compare to, and I'm embarrassed to say I've just forgotten.
So the state, what is the nature of the state that you get in the system? Do you get power law, special function?
Well, remember, this for example, is a chain of H50, so, but we haven't really looked. But again, if you're, we're approximating the self-energy in real space, right? So if you like, we only have a small number of K points. So as you increase the number of approximants, the size of your real space cluster, you start to develop the power laws that you expect. But if you're doing a two-site approximation, you can't see a power law because you have no momentum dependence. And there is a literature of people who do these things in one dimension, seeing how the power laws develop as you increase the number of approximants. I'm sorry?
Can
Oh, yes, yes, yes. So again, the fact is that if you just look at this CDMFT curve, that's these red things, it's quite close to the exact answer, right? And in a way that's surprising, because if you go back to this picture, right, we're keeping this intersite interaction dynamically, and we're treating this intersite interaction by Hartree-Fock, right? This approximation intrinsically has broken translation invariance, and part of that is treating different interactions which are physically equivalent in an asymmetric way, right? So the theory includes the effect of this guy more or less exactly this guy by Hartree-Fock. Nevertheless, the total energy comes out to be quite good, right? So what it's doing is somehow making this, the dynamical part of this, twice as big as it ought to be from the exact solution to compensate for the fact that this is 0. And it just does that automatically. That's what I mean about, in some way, it's being smart. This brutal approximation of breaking translation invariance, both on the level of Green's function and on the level of interaction, is surprisingly less bad than you might expect. Yeah? I think let's discuss that offline. I'm not quite sure what you mean. I mean, that what I understand is really precisely this, just that you keep some matrix elements and not others. And that's just the way it works, right? And as you make bigger clusters, you keep more matrix elements, and the ones you're neglecting are less. But okay. So anyway, this is what I said. There's another thing I want to point out. There are a number of materials which have a natural dimerized or supercell structure. These are 2 examples, right? This is this Ti2O3, for example. The crystal structure is fairly complicated, but there's a natural pair of titanium dimers that you can identify. So in that case, these CDMFT approximations don't break translation invariance in the sense that the crystal structure already breaks translation invariance. It happily treats these dimers, right? It's still true that it treats this intersite interaction dynamically, and let's say this one or that one by Hartree-Fock, right? But it's still a quite reasonable and interesting set of approximations. Okay, now, the alternative representation that we know about is a momentum space representation, which goes by the name DCA. Right? It was introduced by Krish, Mark Jarrell, and other collaborators in this paper. All right? And here what you do is you coarse grain in momentum space. How you think about this is you take your Brillouin zone. I drew a 2-dimensional one here. All right? And you simply tile it into n patches of equal area. So here's 1 patch. Here's 16 patches. Right? And you approximate your self-energy as a piecewise constant function. So it's one thing in this patch and another thing in that patch. Or one thing in this patch, one thing in this one thing in that one. All right? So your self-energy, which is in real life a function of continuous momentum, is now a piecewise constant function. And in the same way, this f function now relates a k state in the lattice to one of these coarse-grained k's, right? And if the function is essentially this, that this thing is 1 if this momentum is in the patch whose center is here, and 0 otherwise, and so on. Ah, very good question. And as you can sort of see from this, there's a lot of flexibility. Basically, they need to have equal area, right? So they can be flavor indices and obey the right fermion commutation relations. And they have to cover all of momentum space. After that, you can do it any way you want to, right? And the formalism still goes through. Now, my belief, and we fooled around with this a little bit, but it basically made me nervous, so I stopped. My belief is that you should do it in a way which respects the point symmetry of your solid. So for example, all of these things are a square lattice, and every one of these patchings obeys all the symmetry of the square. You don't have to do that. You could put, a rectangle here, a square here, and so on, as long as they have equal area. Similarly, and this was pointed out by Antoine and his collaborators, you don't have to do this nice square. You can make this central one a different shape. There's no problem with that. So as long as they have equal areas and cover your momentum space, you're fine. But as I say, my strong prejudice is that they should respect the point symmetry of your problem. Okay. Again, the price you pay in the interaction, so there's two prices you pay. In the CDMFT real space case, you broke translation invariance. You only kept some momentum and not others. In this approach, you approximate a continuous function of momentum by a piecewise constant function. Again, just as in the CDMFT thing, there people advocate periodizing, reconstructing a periodic function. In this DCA thing, there are people who advocate essentially smoothing these discontinuities. And again, in my view, just that the momentum space discontinuity, the piecewise constant nature, is part of the price you pay for the approximation. And you should just live with it. Similarly, what you're doing in effect in the interaction is evaluating your interaction matrix element, which is a function, a continuous function of all momenta, at a discrete set of k points. Right? Again, if you have the Hubbard interaction, which is purely on site, then this thing is just independent of momentum, and then it doesn't matter if you discretize it. As you go to longer range interactions, you're doing this sort of violence to the interaction matrix element. And again, that's part of the price you pay for doing this approximation. Then you do exactly the same formalism. So now your self-consistency condition is your quantum impurity model Green's function for a given patch is just the average over that particular patch of your lattice Green's function with this self-energy. And again, you see that single site means there's just one patch that covers the whole momentum space. Cluster is more patches. It's all the same family of approximations. And the question is, how much can you pay to do the solution? And how much precision do you want on the momentum dependence? All right? And that's a qualitative trade-off that you have to choose. Okay, now, as the number of approximants goes to infinity, you recover the solution to the full model. All right? And there are formal results. There is a discussion, and there was some, actually, in my view, tedious and ultimately relatively pointless argument between the practitioners of CDMFT and DCA about the precise nature of the convergence. In most cases, it's not really interesting because you can't get to big enough system sizes to see the power law anyway. Right? But I believe that when all the dust settled, the statements are that as a formal matter, the corrections to this momentum space thing are basically 1 over, if you like, length squared. That is to say, 1 over your number of approximants to the power of 2 over d. Right? And in CDMFT, it's 1 over n to the 1 over d. That is because you're just doing a coarse graining your problem scale like the boundary. Okay. So one other little point, particularly in this momentum space thing. As I said, you have no problem coarse graining your interaction if you have a purely on-site interaction. Right? If it's independent of momentum, it doesn't matter whether the momentum is continuous or discrete. You can, in principle, treat longer range interactions, just the number of interaction components grows rapidly. Right? There's some kind of momentum conservation, so you really have 3 independent momenta. Right? So that means that you have n to the power 3 different interaction matrix elements, all of which have to be treated in your numerics. I'm told, I haven't tried to do this myself, and maybe there are experts in the audience, that you can put this into the solution of your impurity model, but you get a horrible sign problem. So in principle, you can start to address in this coarse-grained way longer range interactions. In practice, the technical problems are apparently very severe. Okay. Now, you can imagine other formulations, right? This is the general thing that I introduced you to before, all right? And I showed you 2 things that work. The general conditions on this are not known. And it may be that for different problems, there are other choices which are interesting and smarter. or indeed other choices of basis rather than just momentum space or real space site basis. To repeat, this really hasn't been thought through, and it would probably benefit by some creative thought from some formally powerful person. There are two considerations. All right. One, which in my view is the subject of a number of misleading statements in the literature, has to do with causality. Right? Now, you know that if you're solving a quantum field theory, then causality means that the imaginary part of your retarded self-energy always has to be positive. If you like, electron spectral functions have to be positive definite. All right? So this is a condition, if you're solving a quantum impurity model, then this is a condition on the self-energy of the quantum impurity model. Of course, that guy always has to be positive, its imaginary part, so you get a positive spectral function. All right. Now, of course, if you're constructing a lattice, you want to use this to construct an approximation to your physical self-energy, sigma alpha alpha. You would like that physical self-energy to always have an imaginary part which is positive. But sometimes that doesn't happen. All right? In particular, as you probably know, if you make any kind of orthogonal function expansion, here I gave an example of just a cosine expansion in real space, all right? You get ringing. If you're trying to approximate a step function, let's say, by a finite number of orthogonal functions, you get overshoots, and therefore you find small regions of negative self-energy, particularly at band edges, if you try to use this kind of orthogonal function expansion for your self-energy. So in my view, that is mildly annoying, but not a fundamental problem. It's not a fundamental problem because the thing that you're really mathematically solving for is the impurity model self-energy, which is always positive definite. Right? But you can see this ringing phenomenon if you try to make an approximation in terms of orthogonal functions. Yeah?
But can that lead to problems? Because in your self-consistency equation, you typically have the sum over, you take into account sigma alpha alpha from this thing. That can lead to...
Okay, so in my experience, it does not. You have to be a little bit careful with numerics, but because this is positive, and the self-consistency and therefore the Green's functions have positive, of the impurity model have positive spectral function, the self-consistency works out such that when you average over this little negative part, it still keeps the thing you're computing positive. So I never found a problem with that. But of course, when you start computing other things, you have to be aware that this is there and know to not include it, or at least to think about its consequences. But on a formal level, I don't think there's a problem. And it's because this is always positive definite. It really is just a ringing. All right. There is, however, a more subtle problem. And I believe you've been told about Mott insulators. So I hope that this isn't too sketchy. In a Mott insulator, the characteristic feature of a Mott insulator is that the electron self-energy has poles at some frequency near zero. What these poles do is push states away from the chemical potential, opening up a Mott gap. Right? And in general, in a Mott insulator, you expect that at each, let's say, momentum point, if these alphas are momentum, you have one pole. So you come down from high frequency, you have structure, you hit a pole at some energy, then it goes off to negative frequency. Right? So that at each K point, you have one pole. Okay. Now, if I'm doing this dynamical mean field procedure, right, then if it's describing a Mott insulator, then your impurity model approximants will have poles also. So you push states away from zero frequency. And now, when I try to put these guys together to construct this, I have to be careful because I need to have only one pole in each of my real space channels. So therefore, the purely diagonal part of this f function, right, has to only, the f function has to couple only, if I look at the part which is diagonal in my physical index and in my impurity model index, right, this guy then has to be essentially a delta function. I have to couple only one a to each alpha so that I only have one pole here. If this guy has a diagonal part which is made up of more than one of these guys, then it will have more than one pole. And if you have more than one pole, then you have a very bad structure in your Green's function. Here's a self-energy with two poles, one here and one here, right, which I just drew. All right? So if you then put that self-energy, which has two poles, into your spectral function, you will discover that if you have two poles, your self-energy crosses 0 somewhere, and therefore you get a state. So having two poles means you get states in the gap, which shouldn't be there. Right? This is a consequence of a bad dynamical mean field kind of approximation, which associates more than one impurity model state to a given K state. Right? So that's a condition that you have to avoid. Right? And that's really the extent of my general knowledge about what forms of these parameterization functions are allowed. Right? So beyond that, it's an open question and I think worth investigating. All right, so now look, I'm nearly at the end of time. If you guys have the patience, I would like to show you very quickly a little bit of what we know about the accuracy of these approximations, and then make a few remarks about what so far can really be done. Right? So I'm just going to skip over getting things which are different from, which go beyond the single particle Green's function, and ask a little bit about what can be done in practice. All right? So you have to solve a quantum impurity model. You have heard in this course, and we'll hear more about the methods that we have to actually do it. I just want to say that basically we have two numerically exact methods, so-called exact diagonalization and Quantum Monte Carlo. They both have an exponential wall, which limits what you can do. All right? And that constrains your possibilities for this cluster dynamical mean field theory. Right? In exact diagonalization, you represent this impurity model, which has some finite number of sites coupled to a continuous bath of states. You represent the continuous Hilbert space of bath states by a small number of discrete levels. So that's an approximation. And then that gives you a finite problem which you just diagonalize. The size of this approximation, therefore the number of states that you can use to approximate your bath, is controlled by how big a thing you can diagonalize. So in general, because all these problems scale exponentially, if you have n sites in your approximation, right, and you want to keep m bath levels per impurity, then the total size of your Hilbert space, this is the 2 is for spin, is 4 to the m plus 1, that is number of bath sites plus 1 for the impurity, times the number of impurity sites. So that means that you can't really do more, because the biggest you can make this the product m times n and still solve things is about 15. The biggest you can do is 4 sites with 2 or 3 bath orbitals per impurity. All right. Now, there's another interesting open question, which I just want to allude to briefly, even though I realize that this is overburdening this lecture. These quantum impurity models, just viewed as a general quantum mechanical problem, have an interesting sparsity structure. Right? I have a small number of interacting sites coupled to a non-interacting bath. Right? So if I view this just as a problem with some number n plus m orbitals, right, only a small subset of my orbitals have interactions on them. All of my bath orbitals do not have interactions. So that implies some kind of sparsity structure in this problem. Right? The basic brute force exact diagonalization methods we have completely ignore this. They just say we take this problem, we write it as a big matrix, we diagonalize it. Right? But it should be possible to take advantage of that sparsity structure. There have been a few attempts in this direction, which are here. I won't discuss it in detail, but I'm sure that there is something more to be done along those lines. Okay, now Monte Carlo is the other thing. Again, you'll hear a lot about this in this course. Basically, there are two principal flavors. One in which you expand in the hybridization expansion, where you expand in the hybridization between the bath and the impurity state. All right. And this is, again, brutally limited, because to make this thing work, you have to be able to exactly diagonalize your impurity model, and then you have to do a Monte Carlo in the space basically of matrices, which are the size of the Hilbert space of your impurity model, right? And so the practical limit is you can do impurity models which have n of 4, 5, 6, 7, not much more. So again, that strongly limits you in the size of clusters that you can study. The alternative, oh, and the other important thing, and this goes back actually to Tanusri's question. Well, these impurity models are characterized by a hybridization function, which comes from this. If the hybridization function doesn't commute with the basic energy, or more generally, if the hybridization function at one frequency doesn't commute with the hybridization function at another frequency, right? That means that in some physical sense, you can have loops where an electron leaves one site on the impurity, goes into the bath, and comes back onto another site. Those loops create a disastrous sign problem, right? And they're generic when you start to do cluster dynamical mean field theory in this hybridization expansion formulation. So as far as I know, these hybridization expansion methods, except in a few very restricted situations, have not been very successful because of this lack of commutation, meaning that your solution of the quantum impurity model has a terrible sign problem. Yeah. Because this non-commutativity is generic to clusters.
In what sense does CTQMC suffer from the exponential wall?
Oh, for example, it has a sign problem.
Yeah, so that means that if you run it for longer times, it is bound to have a sign of 0.
Correct. It has. Again, it's an interacting fermion system. So as long as it's has enough internal structure to have loops, it will have a sign problem, and the expectation value of the sign will go exponentially to 0 with size of the system and inverse temperature.
So the measurements must be made at some intermediate time scale.
Correct.
Okay.
Well, yes, and if you're if you're at a non-zero temperature and a non-infinite system size, your expectation value of the sign is non-zero, although it becomes rapidly small, right? And 1 over that expectation value of the sign is essentially the amplitude of your errors. So you just have to measure longer and longer and longer as you make your temperature lower or your system size bigger. And the amount more you have to measure grows exponentially. But that does bring up an interesting point, which I'll come back to in a second. The other thing you can do is this sample the interaction perturbation theory. Right? This can be done very efficiently for the Hubbard model now, thanks basically to work of Emmanuel Gull. Much less efficiently for things which are not the Hubbard model. All right. So I'd like to show you just a couple of quick things about the Hubbard model where, because of these efficient methods, you can actually reach quite large clusters. So the work here has really been done by Emmanuel Gull in collaboration with Nikolai Prokofiev, Boris Vistanov, Zhenya Kozik, and Loda Polit. So this is an example of a weak coupling problem where there are alternative approaches which give you essentially exact self-energies. Right? So this is the self-energy obtained as a function of momentum around the Brillouin zone obtained by an essentially exact method. Here you see that you go from single-site dynamical mean field theory, where things are independent of momentum, 4-site, 8-site, 16-site, etc. I guess this is 16, 32, this is 4 and 8. So you can see how it converges, and you can see that except at special momentum points, the momentum dependence of the self-energy, while rather modest, gets captured between 8 and 16, roughly. Yes, I believe it was. Well, this is this diagrammatic Monte Carlo that Prokofiev and Svistanov do. It has different diseases, but the half-filling is not particularly a problem. This is the three-dimensional Hubbard model. They did this at half-filling. You can also do a bit away. They were able to go up to 100 approximants at an interaction, because this is the three-dimensional Hubbard model, of about 2/3 of the bandwidth. All right. Again, you can compute the self-energy, single-site, 18-site, 84, 100, and you can see how it's converging to some non-zero momentum dependence. And finally, you can calculate energies. So this is energy versus system size to the minus 2/3. This is n to the 1 over n to the 2 over d that I told you before. Single site, different size approximants. So you can make an extrapolation for the expectation value of the energy and get a value which is converged with error bars which just come from this fit. So you can see that at these relatively simple situations, interaction not too much bigger than half the bandwidth, temperatures which are relatively high, you can actually access the infinite system size limit and see that this actually works, that it does converge to something, the convergence is what you expect, and this rather complicated plot is just to show that in cases where we have alternative exact answers, this extrapolated value agrees with the exact answer. Right? So in some sense, the process works. Yes?
Computer were these done on?
Sorry?
On what size computer were these calculations done?
This was one of the Swiss ones. In fact, as a numerical thing, this in particular, once you do this interaction expansion for the Hubbard model, it's embarrassingly parallelizable. All right? So what that means, I should say that in every case, all right, quantum mechanics is about matrices. Right? And all of these quantum Monte Carlo things, in some level, somewhere wind up manipulating matrices. Right? And so the question is, you can do calculations very easily, provided that your matrices are small enough to fit into the cache of one processor. Right? So for all of these things, the practical limit of these calculations, all right, is matrix whose size grows with interaction strength and with inverse temperature, fits into the cache of a processor. Right? Once you have that, it's embarrassingly parallelizable, meaning that the startup times are essentially 0. You don't have to coordinate, so you just take as many processors as you have, run Monte Carlo for all of them, add up the thing at the end, and average. So, you know, the size of the computer is really how many independent processors you can get your hands on. And these things tend to be 1,000, 5,000, 10,000. Other stuff which I won't have time to show you because I'm grossly over time now, studying, for example, the superconducting state of the two-dimensional Hubbard model, we tend to use its US NSERC capacity computing, but not really the leadership computing. So we tend not to be able to get or need time on Jaguar, for example, if that's a useful. But the limit on this is really when the matrix gets big enough to overflow the cache. Once your operations have to involve different processors with different caches talking to each other, then all this efficient stuff falls apart. Dynamical mean field solution of the Hubbard model with some n-site dynamical mean field solution to just taking a finite Hubbard model cluster of n sites and simulating it. Right? So here's the expectation value of the sign at different temperatures. These things here, the filled symbols, are just straightforward lattice quantum Monte Carlo at temperatures of a 5th, a 6th, a 10th. What you see is that as you go from a 6th, a 5th, a 10th, a 5th, a 6th, a 10th, the sign, expectation value of the sign drops very rapidly. Right? This is exponential, on a linear scale, the expectation value of the sign. So this is this exponential dependence. Right? The sign expectation value of the sign rapidly becomes extremely small. Okay? Now you do exactly the same thing, only in the dynamical mean field approximation. You still see the exponential drop of the sign. Right? But clearly, the argument of the exponential is much less. Right? It's still going to be dropping exponentially. But what's inside that exponential, it's still system size divided by temperature, but the coefficient is a lot less. So you can do, in effect, bigger sizes with dynamical mean field theory than you can do just doing straightforward quantum Monte Carlo. The sign problem is somehow less. Now, the physical reason for this, I believe, is that in dynamical mean field theory, you have a cluster which is coupled to a bath. Right? So you have an electron which can hop from your cluster into the bath, and then it's replaced by a different one. So that process decoheres the quantum mechanics. right? The electron that comes back from the bath is uncorrelated with the one that went into it. So this dynamical mean field thing, in effect, decoheres some of the quantum mechanics. All right? And that makes the sign problem much better. Right? And it's part of the reason why one can go to much larger clusters and why Emmanuel and these guys were able to do these heroic calculations. Right? And we saw, right, that at relatively high temperatures, you do get convergence to known answers. So even though you've decohered some of the quantum mechanics, you still get the right answer. Right? But it makes me wonder about the convergence of this process. Right? Because it's clear, just from these differences in sign, that the quantum mechanics of these two problems is not the same on the level of a finite-sized cluster. Right? And so you may ask, is the quantum mechanics the same as the system size goes to infinity? Right? This issue has not had a proper theoretical attention. My belief is that there is an order of limits issue, and that this cluster dynamical mean field thing, which we have defined, at a fixed non-zero temperature, as you take the number of approximants to infinity, it will converge to the exact answer. But that if you take the temperature goes to 0 first, and then n goes to infinity, you may not be guaranteed to get the right answer. And that in particular, subtle quantum mechanical things, such as topological terms in your action and topological surface states, may very well not be captured. Now that's just a speculation. Again, this is not known. Right? And it's probably worth thinking about as people consider what this class of approximations means. All right, so that's what I said here. And I think that this is a good place to stop. I'm sorry I ran over, and I hope that this was at least a little bit useful.
Your last remark, is this somehow related to the similar, well, behavior if you think about thermalization in a non-equilibrium system, that you have to, for a fixed time, the system size go to infinity first and then time to infinity? Is that related?
That's an interesting point. I haven't thought about that before, so I don't have a good answer. It's certainly conceivable. Although there's a separate set of things which were implicit in Philip's talk and which various people have been going around in circles on. I don't know if Philip is here or if he wants to comment, but it's a different set of questions. Is just, given that you're coupled to a bath, what does it mean to be in a non-equilibrium state? If you're in equilibrium, it's clear. You have a system and a bath, and they're all in thermodynamic equilibrium. But once you're doing these dynamical things, where does the energy go? What does it really mean to quench things? How does it equilibrate? What's the role of the bath? These are interesting questions which I think are not theoretically settled.
About you have this hydrogen atom chain problem, that you calculated the total energy. So is it like you have done really a self-consistent DMFT calculation?
Yep. So what we did, to be very precise, was we took some set of n theorist hydrogen atoms arranged in some positions in space. For this purpose, it doesn't matter what. We retained, they're theorist hydrogen atoms because we retained only the 1s state. And for professionals, it was this STO 6G basis, whatever that exactly means. But some approximation to the 1s state. We computed all the Coulomb matrix elements, all the matrix elements of E squared over R between these states. We then did, in one of these CDMFT kind of approximations, we treated the matrix elements within our little supercells dynamically, all the other ones by Hartree-Fock. Then you have to do a self-consistent calculation because that gives you a problem. You solve first the Hartree-Fock problem, that gives you a density matrix. You need to solve Hartree-Fock to get density matrices to get the expectation values. Then that defines a dynamical mean field problem. You solve that. Then from the self-energies, which have Hartree terms for the part which is outside your block and dynamical terms which are inside, you compute the density matrix, you re-update your Hartree-Fock, and you keep doing that until things converge. And then once you do that, then you compute the energy by using standard many-body formulas. So that's what we did.
What was M? That means it was not dependent on, in the hydrogen problem, it was not dependent because the number of sites that you took was not important.
Okay, well, yeah, there's a separate story which I didn't have time to discuss, which we were interested in at the time. But in my general notation, capital M is the total number of single particle states in the system, right? So in the hydrogen atom problem, because we just have one state per hydrogen atom times 2 for spin, M is just the number of hydrogen atoms, right? And then we have dynamical mean field approximations, which are n equals 1, that single site, n equals 2, n equals 4. And then we considered various cases. The picture I showed you happened to be for m equals 50, but we also did 6 and 8 and 4. And so, and we wanted to see how things depend on m and n, but that's a separate story.
How is M coming into the problem?
Well, via the self-consistency equation. Can somebody turn on the lights for a second? Oh, okay, all right. So your physical Green's function is some m by m matrix, right? If you have m degrees of freedom in real space, right? Then if I had a translation invariant system, I could Fourier transform it, and then it would typically be diagonal, and I would have m k points. So this is where m comes in, right? Then n is your number of self-energy approximants, right? So your self-energy is an m by m matrix, right? Same size as your Green's function, right? But the entries in this are determined by this much smaller number of things, right? So then you have a self-consistent equation which says that you take your G, which is m by m, and then you collapse it in the way dictated by this F, right? So you trace over your m indices to get an n by n matrix, which is in your self-consistency condition. So the m is living in here in the self-consistency condition. Of course, if you do this for a system with a translation invariance, like a lattice, right, then you use translation invariance to ignore this structure, right? Then you just have a Green's function, which is a function of momentum. So it's just a diagonal thing, and this collapses into some kind of average over different regions of momentum space. But in general, your m is the Green's function, and the computational thing you have to do is get the m by m Green's function and then collapse it according to whatever your function is.
And can you have one disorder within this cluster?
Yes. Yep. At this very general level, there's no translation invariance, so my m sites could all be different, right? So disorder is allowed in that sense.
Even within the small n?
Oh, no, wait. Let's be very precise here. So here you have a Hamiltonian. Let me just back off one step. I presented to you two ways of doing this cluster dynamical mean field theory. One is this momentum space thing, right? That disorder is very awkward to include, right? It essentially assumes translation invariance because it really assumes that k is a good quantum number. If you want to consider disorder, then you have to start considering matrices with off-diagonal components in k space, and it just becomes a big mess. But if you take the real space component, then you have disorder that puts randomness inside here, right? Different sites are different. But each of your self-energies, if you go back to your supercell, right? Here is some abstract representation of a two-site approximation. These two sites could have different local potentials than these two. So then there will be a self-energy here, self-energy, right? Each of these self-energies is determined by two things, right? The problem is simplified because we're not including these approximations to the self-energy, but the randomness will show up because this self-energy will be, or the breaking of translation invariance will show up because this self-energy is different from that one. right? And it all just falls out naturally from the machinery. You just put in this, you do this, and it works. So in fact, these molecule things we did, if you're considering a chain, it has ends, right? So the sites near the end are different from the sites in the middle. And that is included in the energy calculation, and it just, so there's no conceptual problem. There's a question of accuracy. And in fact, going back to this order of limits business, the subtleties associated with disorder in low dimensions, Anderson localization, the mesoscopic physics fluctuations, and so on, are not well captured.